This lecture provides an introduction to two fundamental operations in convolutional neural networks: convolution and max pooling. Convolutional neural networks, or convnets, are a type of deep learning model particularly good at handling grid-like data such as images. They take inspiration from the way animal visual systems work. The convolution operation is a core part of convnets. It involves using a small filter, also called a kernel, and sliding it over the input data. At each step, it calculates a dot product. This process helps in pulling out important features from the data. The mathematical formula for 2D convolution involves summing up the products of the input and the kernel values over a specific window. To visualize this, imagine a simple example with a small input image and a 3x3 kernel. By sliding the kernel over the image and performing the dot product at each position, you get a smaller output called a feature map. The exact size of the feature map depends on how you handle the edges and the step size of the kernel. We can see convolution in action using a real example from the scikit-learn digits dataset. We load an image of a digit and apply a simple edge detection kernel. The code imports necessary libraries like NumPy for numerical operations and SciPy for the convolution function. It then loads the digits dataset and selects the first image. A 3x3 kernel is designed to highlight edges. The convolve2d function from SciPy performs the convolution. Finally, the original and convolved images are displayed side by side using matplotlib, showing how the convolution operation brings out the edges in the image. Next, we explore the max pooling operation. Max pooling is used to reduce the size of the feature maps, specifically their width and height. It works by taking a sliding window over the input and selecting the largest value within that window. This helps to decrease the number of calculations needed and also makes the network a bit more resistant to small shifts in the image. To visualize max pooling, consider a 4x4 input matrix. If you apply a 2x2 max pooling operation with a step size of 2, you divide the input into 2x2 blocks and take the maximum value from each block. This results in a smaller output matrix containing these maximum values. We can implement a simple max pooling function using NumPy. The Python function takes an input array, the size of the pooling window, and the stride or step size. It calculates the dimensions of the output array and then iterates through the input, applying the max operation within each pooling window to produce the output. We apply this function to the same digit image we used before with a 2x2 pooling size and stride. The code then displays the original image and the image after max pooling, showing how the pooling operation reduces the resolution while retaining important features. In conclusion, this notebook introduced two key operations in convolutional neural networks: convolution and max pooling. Convolution helps extract features using learnable filters, while max pooling reduces the spatial dimensions of the feature maps, lowering computation and adding robustness to translations. When combined in multiple layers, these operations form the foundation of powerful convnet architectures capable of understanding complex patterns in image data.